This video, I'm going to go over section 12.1, inference for linear regression. So we're talking about confidence intervals, we're talking about significance tests. So we're going to look at conditions, we're going to revisit interpreting some things in context and look at some new, and then do the confidence intervals and the test for the true slope. With the sampling distribution, I'm not going to get too much into things here. The mean of all of the sample slopes is equal to the true slope, which we use the Greek letter beta for. The sample standard deviation is given by this formula here, which I'm looking at the formula sheet right now, is provided for you on the formula sheet. And then you have your 10% condition and you have your normal condition. So we're going to look specifically at that in one of these next sections. Okay, conditions. There's 5. And because we're dealing with a linear equation, we're going to just use LINER, L-I-N-E-R, for an acronym to help you remember your conditions. So the L stands for linear. There's 2 things that we want to state here. We're going to state that the scatter plot is straight, or the scatter plot is linear, and then the residual plot shows no pattern. Obviously here the scatter plot is roughly linear, but the residual plot does show a pattern. That would be a problem. We're checking both of those for the linear condition. Independence is essentially because you're selecting without replacement, you're checking the 10% condition. Been there, done that. Normal. This is going to be, you're going to look at the distribution of the residuals. It could be a dot plot, histogram, box plot, stem plot. Most likely you're going to see a dot plot or a histogram. You're looking for no strong skewness or outliers. Equal standard deviation. What you're doing there is you're looking at the residual plot and you want to see consistent variability like you do in this residual plot on the left. This variability is not consistent. You start with small residuals and then they get larger and larger. So that's what they mean by equal standard deviation. And then random, the random condition. Was it a random sample or was it a completely randomized experiment where there's a random assignment? That's what you're going to look for. So the conditions are completely different than the ones we've seen. Obviously, there's some overlap with the 10% normal and random, so I guess I take that back. Not completely different, but a little bit different. So that goes through that. Let's move on. Okay, the likelihood that you're going to have to use any of these formulas on your formula sheet by hand, pretty low. They would need to give you some summary statistics, and you'd need to know some sample standard deviations, the sample size, or the population standard deviation to do this. So that's unlikely, so I don't want you to get caught up in that. We're going to be looking at how to do a confidence interval first. So confidence interval, the structure is still the same. This is directly off your formula sheet, your statistic plus or minus your critical value times the standard deviation of the statistic. That's what it's always been. There's 3 parts. So our statistic is going to be our point estimate, or if we want to know the true slope, the population slope, we estimate it with the sample slope. So this lowercase b, plus or minus critical value, because we have quantitative data, we're using the t-distribution. So this would be inverse t with a certain degrees of freedom. And then the standard error of the slope. And this is going to be something you're going to pull from the computer output in almost all instances. This formula is on your formula sheet. It doesn't say standard error. It just says S sub b, but the heading is standard error. But unlikely that you're going to have to calculate this by hand. You'll notice here, this is something new. There's the degrees of freedom are now n minus 2. And you might be asking, well, why is it n minus 2 and not n minus 1? The reason is the least squares regression line has a slope and a y-intercept. So there's 2 parameters we're estimating. So that's why we have n minus 2. Okay, so this is what you're going to see quite a bit of. You're going to see a Minitab output. Standard error of the slope, you'll notice SE stands for standard error of the coefficient. Well, you have the constant, which is the y-intercept, and then your explanatory variable. The number in front of the x is the slope. So this is the standard error of the slope. I'm sorry, this is the slope. This is the standard error of the slope. So The idea there is, you'll notice here, it's going to sound a little bit familiar to confidence level. If we repeat the random assignment many times, the slope of the sample regression line varies by about 0.002 from the slope of the true regression line. And then they put some context at the end. So that's a new skill. Find the critical value, 95% confidence. That would leave 2.5% in each tail. And our degrees of freedom here, we had 70 helicopters, minus 2 is 68. So I'd do inverse T of 0.025 with 68 degrees of freedom, which you see there. Part C, part B, we're still finding the confidence interval. So it's going to be our point estimate, the sample slope, plus or minus that critical value I just spoke about, times the standard error, which is right here. We don't need to do any calculation with that, which is really kind of convenient. So you'll notice that's the same number right there. Add and subtract your margin of error to get this. Interpretation, we're 95% confident that the interval from this to this, we have units because it's quantitative, captures the slope of the true regression line relating x to y or y to x. That's the same structure as it's been. Part D, interpret the meaning of 95% confidence. That's another way of asking for the confidence level. So if we repeat the experiment many times, about 95% of the confidence intervals we create are going to capture the slope of the true regression line. All right. They just go through an example here. They go through the conditions. You'll notice here for linear, they mentioned the scatter plot and the residual plot. They're checking the 10% condition. For the normal condition, they're checking the histogram of the residuals. Well, it's not perfectly symmetric, or you could argue it's not symmetric. It's not strongly skewed, or are there any outliers? The equal standard deviation, your residuals are pretty consistent in their variability. They're not getting larger or smaller as they go on. And then, I lost random. Oh, it was a random sample of 16 trucks. So that's just another example. This goes through, if they give you the specific data, how to do this on your calculator. Under the stat test menu, there's something called a linear regression t-interval that you can substitute the values in. But it's unlikely, it could happen, unlikely they're going to give you all of the data. Okay, usually you're going to see something like this. So what I would do is pause the video here after I'm done talking and see if you can run through the confidence interval, just the do step, and then come back when you're ready. All right, so my point estimate is going to be the slope, this negative 0.003, plus or minus. I need a 95% confidence interval, and I know that my sample size is 16. I have 16 adults. Minus 2 is 14, so I'm going to do inverse T of 0.025 comma 14 to get my critical value times this standard error. Times this standard error here. And for some reason I can't scroll down to see the bottom of this, which is weird. Okay, well, hey, there we go. All right, 14 degrees of freedom, so there's your confidence interval that you end up with. And then you'd go through your state plan to conclude. I didn't really talk about those. The state is beta. That's the true slope, the slope of the population regression line relating y to x or x to y. We talked about the plan step, your conditions already. The name is a one sample t interval for the slope, or eventually we're going to talk about a one sample t test. And here we go with that. From your formula sheet, same generic formula as every other test we've done this year. It's your statistic. Your test statistic is your statistic. So in this case, the sample slope, B, minus the parameter, beta, which in most cases will be 0 from the null hypothesis, divided by the standard deviation of the statistic, which will be actually the standard error of the statistic. And you'll find that directly on your formula sheet, or in most cases, it'll be on a Minitab table. All right, so you'll see something like this. And let's see what they asked us here. Okay. Do the data provide convincing evidence of a positive linear relationship? So the null would be that the slope is 0. There is no relationship. So beta equals 0. The alternative would be that beta is greater than 0. We have a positive slope because of a positive linear relationship. Conditions, I'd go through the same exact conditions as I did for a confidence interval. And then for the name of the test, it would be a one sample t-test for the slope. For the do step, I'm going to just use the output from the mini tab. I'm going to take the statistic, the slope, 1.4929, minus 0, the null value, divided by the standard error, this 0.48. And the cool thing is, this is going to tell you your test statistic, and this is going to be a two-sided p-value if it's a two-tailed test. So when I do that minus 0 divided by that, I'm going to get 3.07. That's what's going to happen. And if I did TCDF, from there I could get the p-value. Okay, so you'll see here, did they show the calculation for that? Huh. Oh, that's sad. Oh, duh, here it is. The slope minus 0 divided by the standard error, that's where that comes from. And then if you do TCDF from 3.07 to infinity with 36 degrees of freedom, that's where your p-value 0.002 comes from. Just to reiterate this, when you see the table, this is going to be a two-tailed p-value, unless they specify otherwise, but it's always defaulting to two-tailed. How to do the test on the calculator, if they give you all the raw data, goes through that there. And check your understanding. You can run through this, pause the video now, and then I'll just do the do step. So on the do step, it would be this minus 0 divided by this, which gives you about negative 4.64. And they want to know, is there a negative relationship? So I would do TCDF from negative infinity to this negative 4.64, comma, the degrees of freedom, you have to click there to figure out how many there were. I think there were 16 people in that study, so 14 degrees of freedom. Could be wrong, going off of memory. So summary of this section, we're doing regression inference. So confidence interval for the slope and a test for the slope. Conditions are linear. We went through those already. You're going to have to be able to construct a confidence interval and a test for the slope. The one thing that I covered once that I don't see here, you're going to need to know how to interpret that standard error of the slope as well. That's like if we repeat the random assignment many, many times, that's how much the sample slope is going to vary from the true slope. So that's it for section 12.1. Hopefully this video was informative and helpful.